name is Professor Orata. We have been having a series of these thermodynamic lectures, and we are still continuing. Now we want to interface the Carnot cycle and the Rankine cycle. Remember the Carnot cycle had four processes. We have the isothermal expansion, we have adiabatic expansion, we have isothermal compression, and adiabatic compression. So we can illustrate that the pressure volume diagram as follows. So state 1 to state 2 is isothermal expansion. 2 to 3 is adiabatic expansion. And 3 to 4 is isothermal compression. And of course 4 to 1 is adiabatic compression. So that is basically the Carnot cycle, if you remember. And in the Carnot cycle, the fluid was the ideal gas. Ideal gas was a fluid, the system, an ideal gas. That is this gas which obeys the ideal gas equation of state, PV is equals to nRT. Now, the question is, can we interface the Carnot cycle? Can we interface the Carnot cycle with the Rankine cycle? And remember that the Rankine cycle like we have mentioned in our earlier lectures, has four elements actually. We have the pump, we have the boiler, we have the turbine, and we have the condenser. So that this can be schematically illustrated as the pump, pumps the fluid, which in this case is not an ideal gas, it is water. The boiler heat is added. Boiler heats the water into steam, can be superheated steam, can be a wet vapor. Normally, dryness fraction is about 18%. So we have the turbine. And we have the condenser. Again, here heat is extracted, QC. And the cycle continues. So you can now you have a pictorial depiction of what we have as Carnot cycle and Rankine cycle. Now, can we interpose the Carnot cycle into the Rankine axis of temperature and entropy? Let us do that. So we have temperature versus entropy. So remember, in the case of Carnot cycle, the axis was pressure versus volume. Now we are talking of temperature versus entropy. So if you superimpose the Carnot cycle into the Rankine axis, then we'll have point will correspond to high temperature, low temperature, S1, S2. So this is state point 1, state point 2, state point 3, and state point 4. Now, there are similarities. From state point 1 to 2, just like in the Carnot cycle, the process is isothermal. Even here, the process is isothermal. And in the Carnot cycle, the state point 2 going to 3 was adiabatic expansion. Now, in this particular case, it is an isentropic process. What does that mean? So that you see that they're actually similar. We go back to Clausius inequality, which tells you that ds is greater or equal to dq over t. And when the process is isentropic, it means that ds is 0. ds is 0. So if you plug in to the equation, then you clearly see that dq over t is equals to 0. And on a constant pressure, remember, constant pressure, dq is basically dh or delta h. So dq is 0, that means the process is adiabatic. And so step 2 to 3, the Carnot cycle was adiabatic expansion, and you see that that's adiabatic. So again, they correspond. And then process 3 to 4 is again isothermal. And that also corresponds to isothermal compression in the Carnot cycle. And step 4 to 1 is isentropic or adiabatic. So that again corresponds to adiabatic compression in the Carnot cycle. So you pretty much see that it's very easy to interpose both of them or juxtapose them. That is the Rankine cycle and the Carnot cycle. Let us move on further and now use that matrix for the Rankine cycle where we had the saturated vapor and the saturated liquid. So we have again still our temperature, and we have our entropy. We have our saturated liquid. This represents saturated liquid. And here represents saturated vapor. As you can see, we have the temperature, entropy, and we have the saturated liquid curve and the saturated vapor curve. So, if we work with this particular matrix, then we are going to see that if we impose the Carnot cycle here, step 1 to step 2, 3 to 4, we realize that if we have to have the Carnot cycle operate in the Rankine domain, then it is important that processes associated with 1 and 2 involve phase transformation, and that in 3 to 4 also involve phase transformation. In this particular case, it will be vaporization, and in this case, it will be condensation. Vaporization means liquid going to gas, and condensation is gas going back to liquid. And why are we saying that? During phase transformations, there is no change in temperature. So for us to have the Carnot cycle operate in the Rankine matrix, that process 1 to 2 and 3 to 4 must involve phase transformations. And that means, in essence, that the fluid which you are going to use now in the Carnot cycle should be either water or steam. Will be water or steam, not ideal gas. Now, let us look at what happens. Now, what happens? You notice that if we start at, we have state point here where we have the saturated liquid, and remember that at that particular point, the dryness fraction is 0.00. What is dryness fraction? We have wet fraction and we have dryness fraction. And it's important that you know what they mean. Dryness fraction is the mass of dry vapor or steam over mass of dry vapor or steam plus mass of liquid in the mixture. And wetness fraction is the mass of water over the mass of mixture. So we are saying that at state point 1, at this particular state point, let's call it X, or on the saturated liquid curve, the dryness fraction is 0. And that makes sense because in the saturated liquid curve, we have the liquid, which has certain percentage, but there is no vapor. And so those are 0, 0. So long as we're dividing 0 by any number, you get 0. And here, it will be 1. The dryness fraction will be 1.00. Now, if you look at your process, where you have the liquid in the boiler, and you have the liquid in the turbine, in the condenser, and the pump, if we have to configure the Carnot cycle to fit into the Rankine cycle, then it means that all these processes must take place in the different elements. That is, the Carnot cycle processes 1 to 2 will take place in the boiler. As you can see, we have vaporization. Then the Carnot cycle step 2 to 3 will take place in the turbine. And the Carnot cycle step 3 to 4 will take place in the condenser. And 4 to 1 will take place in the pump. So all these processes must take place in the different units or systems within the Rankine cycle. If we have to operationalize the Carnot cycle based on the Rankine cycle. And so, you can therefore see that we will have, for example, one of the major challenges other than the fact that adiabatic processes are fast. So when you follow an isothermal process with a adiabatic process, there is always a challenge of sorts, which you mentioned earlier in the lectures on Carnot cycle and the frictional consequences of frictional forces. Now, when we look at this curve, we see that from 3 to 4, we still have vapor here because this is a two-phase region. This is a two-phase region. We have vapor plus liquid. It's a two-phase region, so we have vapor plus liquid. So it means that even at state point 4, we still have vapor, which we must condense so that we come to that state point, which we call, let's call it XM. And when we do that, we can do that and continue with the compression. And remember, when you're compressing, during that compression, a lot of work has to be done. So we can compress from state point XM to XM prime. And then, of course, remember now, the pump, the pressure is significant, and the pump can pump the fluid into the condenser, into the boiler, and then the process continues. So in that particular case, we have now operationalized the Carnot cycle on the Rankine cycle matrix. But remember also that even if, for example, you didn't condense completely the vapor, the system will still be very efficient in its operations, only that it will be bulkier. It will be a lot bulkier. So that is very, very important for us to note. So we can actually interpose the Carnot and Rankine cycles. What I want you to remember is very, very simple. That is, one, now to use the Carnot cycle, the Rankine matrix, the fluid is not ideal gas. It must be either water or steam. Point number one, very important for us to note. Also, we note that the steps 1 to 2 is isothermal, corresponds to constant temperature also in the temperature entropy matrix. The adiabatic process 2 to 3 in the Carnot cycle safely corresponds to the isentropic process, which you have seen is also adiabatic. And of course, the process 3 to 4 also corresponds to an isothermal process, which is also in the temperature entropy matrix, quite correct and in agreement. And then, of course, 4 to 1 is adiabatic. Again, that is an isentropic process. So again, they correspond because that's adiabatic, like you have said, based on Clausius inequality. So that's very, very important for us to note those basic elements. And that all these processes, 1 to 2 and 3 to 4, which involve constant temperature, suggest that for us to tailor the Carnot cycle into the Rankine matrix, then we need to have a phase transformation in the process 1 to 2 and 3 to 4, because phase transformation involve constancy of temperature. We have seen that's vaporization, and we have condensation at that point. And we need for all these Carnot cycle processes to take place in the different elements in the Rankine cycle. And that's why we said step 1 to 2 will take place in the boiler, 2 to 3 in the turbine, 3 to 4 in the condenser, and X prime 1 now will take place in the pump. And so next time we will continue looking at other aspects of the Rankine cycle in terms of its efficiency.